Welcome to this comprehensive guide on machine learning data splitting. Understanding how to properly divide your dataset into training, validation, and test sets is fundamental to building reliable machine learning models. Today we'll explore why we split data, how to do it correctly, and the crucial role each subset plays in the machine learning pipeline. Imagine you are teaching a student for an exam. If you give them the same questions they'll see on the test during practice, how can you truly assess their understanding? They might just memorize answers without learning the underlying concepts. The same principle applies to machine learning models. When a machine learning model sees the same data during training and evaluation, it can memorize specific patterns rather than learning generalizable rules. This is called overfitting. The model performs well on data it has seen before but fails miserably on new, unseen data. The solution is to split our data. We use some data for training the model and reserve completely separate data for testing. This way, we can honestly evaluate how well our model generalizes to new, unseen examples. This gives us confidence that our model has truly learned patterns, not just memorized specific cases. Let's work with a concrete example to understand data splitting. We'll use a house price prediction dataset with features like square footage, number of bedrooms, location, and age. Our goal is to predict house prices based on these characteristics. Here's our dataset structure. Each house has measurable features like square footage and number of bedrooms, plus categorical features like location. Our target variable is the house price. With 10,000 examples, we have enough data to split into meaningful subsets while maintaining statistical validity in each group. Now let's understand the three-way split: training, validation, and test data. Each subset serves a specific purpose in the machine learning workflow, and understanding their roles is crucial for building robust models. Here's how we typically split our data. From our 10,000 house dataset, we allocate 60% for training, that's 6,000 houses the model will learn from. We reserve 20% for validation, 2,000 houses for tuning and optimization. Finally, 20% becomes our test set, 2,000 houses for final evaluation. These proportions can vary, but this 60-20-20 split is a common and effective starting point. Let's start with training data, the foundation of machine learning. This is where your model learns patterns, relationships, and makes generalizations. The quality and quantity of training data directly impacts your model's performance. During training, the model receives input features for each house and learns to map them to the correct target prices. It analyzes thousands of examples, identifying patterns like houses with more square footage tend to cost more, or downtown locations command premium prices. The model adjusts its internal parameters to minimize prediction errors across all training examples. Training data has several key characteristics. It's typically the largest portion of your dataset, usually 60 to 80%. The model sees this data during learning and uses it to update its internal parameters. Quality matters more than sheer quantity. Clean, accurate data beats noisy, abundant data. Training data should represent the real-world distribution you expect to encounter. Diversity in your training examples helps the model generalize to new situations. Validation data serves as your model's report card during development. While the model learns from training data, validation data helps you make crucial decisions about model architecture, hyperparameters, and when to stop training. Think of it as practice exams that guide your study strategy. Here's the validation workflow. First, we train our model on training data. Then we evaluate its performance on validation data that it has never seen. Based on these results, we tune hyperparameters like learning rate or model complexity. We repeat this cycle until we achieve satisfactory performance. The feedback loop ensures continuous improvement without overfitting to the training data. Here's a hyperparameter tuning example comparing different learning rates. Model A with learning rate 0.01 shows good balance between training and validation scores. Model B with higher learning rate 0.1 overfits, high training score but poor validation performance. Model C with very low learning rate underfits both sets. Validation data helps us choose Model A as the best option. The validation data clearly indicates Model A is our best choice. This demonstrates the power of validation data in guiding our decisions. Without it, we might have chosen Model B based solely on training performance, leading to poor real-world results. Let's summarize validation data characteristics. It's typically 15 to 25% of your total dataset. Crucially, it's never used for training the model parameters. Instead, it guides hyperparameter tuning and model architecture decisions. It helps prevent overfitting by providing an objective performance measure. It should come from the same distribution as your training data. However, don't use validation data for final model evaluation, as repeated use can lead to validation set overfitting. Test data is your model's final exam, the ultimate measure of real-world performance. This data should never be seen during training or validation. It provides an unbiased estimate of how your model will perform on completely new data in production. Think of test data as being locked in a sealed vault during development. While you train, validate, tune hyperparameters, and select models, the test data remains completely untouched. Only after all development decisions are finalized do you unlock the test data for final evaluation. This ensures an honest assessment of your model's true performance. Here's the proper test evaluation process. First, complete all development activities, training, validation, hyperparameter tuning, and model selection. Only then proceed to step 2. Test data evaluation. Load the test data for the very first time. Run your final model's predictions. Calculate performance metrics. And report results honestly, even if they're disappointing. This is your model's true performance. Let's interpret different test result scenarios. Scenario A shows ideal results. Consistent performance across all sets indicates good generalization. Scenario B is concerning, good training and validation but poor test performance suggests data leakage or distribution mismatch. Scenario C shows consistent but low performance across all sets, indicating underfitting. You need a more complex model or better features. Here are test data characteristics. It's typically 15 to 25% of your dataset and remains completely unseen during development. Use it only for final evaluation to get an unbiased performance estimate. It should match your expected production data distribution. Always report results honestly, even if disappointing. Crucially, never use test results to make model improvements. And don't cherry-pick favorable results. This defeats the purpose of unbiased evaluation. Not all data is created equal, and different types of data require different splitting strategies. Let's explore various approaches to ensure your train validation test split maintains data integrity and provides reliable model evaluation. Random splitting is the most straightforward approach. You randomly shuffle your dataset and divide it into the desired proportions. This works well when your data is independently and identically distributed, with no time dependencies or grouping structures that need to be preserved. Stratified splitting maintains the same class distribution across all splits. This is crucial for imbalanced datasets. For example, if your original data is 80% class A and 20% class B, stratified splitting ensures each subset maintains this same proportion. This prevents scenarios where your test set might have very few examples of minority classes. Time-based splitting is essential for time series data or any data with temporal dependencies. You split chronologically, earlier data for training, recent data for validation and testing. This simulates real-world scenarios where you predict future events based on historical data. Random splitting would create data leakage by using future information to predict the past. Let's see how to implement these data splitting strategies in Python using scikit-learn. We'll cover random splits, stratified splits, and custom splitting approaches with practical code examples. Here's the basic random split implementation. We use scikit-learn's train_test_split function twice. First, we separate the test set 20% of the data. Then we split the remaining 80% into training and validation sets. Notice we use test_size equals 0.25 for the second split because 25% of 80% equals 20% of the total dataset. For stratified splitting, we add the stratify parameter to train_test_split. This ensures each split maintains the same class distribution as the original data. This is particularly important for imbalanced datasets where random splitting might result in some splits having very few examples of minority classes. For time-based splitting, we manually create chronological splits. First, sort your data by date to ensure proper temporal order. Then use index-based splitting to create train, validation, and test sets. This approach respects the temporal nature of the data and prevents future information from leaking into training. Even with proper splitting techniques, there are common pitfalls that can compromise your model evaluation. Let's examine these mistakes and learn best practices to ensure reliable, unbiased model assessment. Data leakage is one of the most dangerous pitfalls. The first example shows preprocessing leakage, fitting the scalar on the entire dataset before splitting means test data statistics influence the preprocessing. Always fit preprocessing steps only on training data. The second example shows temporal leakage. Using random splits on time series data allows future information to leak into training. Test set abuse comes in many forms: testing multiple models on the same test set and choosing a best performer is a form of indirect overfitting. You're optimizing for test performance. Using test results to make any model decisions violates the principle of unbiased evaluation. The correct approach is to use the test set exactly once, at the very end, and report results honestly without making any changes. Here are the key best practices. Always split data before preprocessing to avoid leakage. Maintain data distributions using stratification when appropriate. Respect temporal order for time-dependent data. Use the validation set for all development decisions. And touch the test set only once. Document your strategy and stick to it. Consider cross-validation for small datasets. Most importantly, report all results honestly without cherry-picking favorable outcomes. Let's explore advanced data splitting concepts that become important as your machine learning Projects grow in complexity. These techniques help ensure robust model evaluation in challenging scenarios. Cross-validation addresses the limitation of a single train validation split. In five-fold cross-validation, we divide data into 5 equal parts. Each fold takes a turn being the test set while the other 4 serve as training data. This gives us 5 performance estimates, providing more robust evaluation than a single split. Cross-validation provides several benefits. It gives more robust performance estimates by averaging across multiple folds. It makes better use of limited data since every sample serves as both training and test data. It helps identify model variance. High variance across folds indicates instability. It's become standard practice for comparing different models fairly. Group-based splitting handles scenarios where data points aren't independent. In medical imaging, you might have multiple X-rays per patient. Random splitting could put the same patient's images in both training and test sets, leading to data leakage. The solution is to split by patient groups, ensuring no patient appears in multiple splits. Nested cross-validation combines hyperparameter tuning with unbiased evaluation. The outer loop performs standard cross-validation for model evaluation. The inner loop performs hyperparameter tuning within each outer fold. This prevents hyperparameter overfitting and provides truly unbiased performance estimates, though at higher computational cost. Let's walk through a complete, realistic example of data splitting for house price prediction. We'll cover everything from initial data exploration to final model evaluation, demonstrating proper splitting techniques throughout the process. This example demonstrates the complete workflow. We start by exploring our data, then prepare features and targets. The crucial step is the initial train test split where we lock away 20% for final testing. We create train validation splits from the remaining data. Pre-processing is fitted only on training data. We develop and compare models using the validation set, never touching our test data. Interpreting results across the 3 sets reveals important insights. Scenario A shows consistent performance across all sets, indicating good generalization. Scenario B shows dramatically worse test performance, suggesting data leakage or distribution shift that needs investigation. Scenario C shows consistent but high error across all sets, indicating the need for a better model or additional features. Let's summarize the essential concepts we've covered about data splitting in machine learning. These principles will serve as your foundation for building reliable, trustworthy machine learning models. Here's our 3-part summary. Training data. Typically 60 to 70% of your dataset is where the model learns patterns and updates parameters. Quality matters more than quantity. Validation data. 15 to 20% of your data guides hyperparameter tuning and model selection without being used for training. Test data, also 15 to 20%, provides final, unbiased evaluation and should be used exactly once. These 6 golden rules will keep your model evaluation honest and reliable. Split data before preprocessing to avoid leakage. Keep test data completely hidden during development. Use validation data for all decisions. Respect your data's inherent structure. Use the test set only for final evaluation. And always report results honestly. This builds trust and advances the field. Proper data splitting is fundamental to building trustworthy AI systems. It ensures your models truly learn generalizable patterns rather than memorizing specific examples. Honest evaluation leads to better models. Reliable performance estimates build confidence in deployment. And proper methodology advances our entire field. Your commitment to rigorous evaluation practices doesn't just improve your own models, it contributes to making AI more reliable and trustworthy for everyone. Here are your next steps. Practice these techniques on your own datasets to build muscle memory. Always document your splitting strategy so others can understand and reproduce your work. Share this knowledge, teach others proper evaluation techniques to elevate the entire community. And most importantly, stay curious and keep learning. The field of machine learning is constantly evolving, and your commitment to best practices will serve you well throughout your journey. Thank you for joining me on this comprehensive journey through data splitting in machine learning. You now have the knowledge and tools to build models that truly generalize, evaluate them honestly, and contribute to advancing our field. Remember, every properly split dataset and every honest evaluation helps build more trustworthy AI for everyone. Keep practicing, keep learning, and keep building amazing things.